Today we're going to look at enantiomers. Now, enantiomers are a type of stereoisomer. Stereoisomers are isomers that have the exact same connectivity, but they differ in their spatial arrangement. So that means that they're going to be in different locations. Now, enantiomers specifically, they're a type of stereoisomer. That means they are mirror image isomers. So if we have this chiral carbon here, and we draw its mirror image, exactly like this. If you try to rotate one of these molecules, it won't superimpose on the other one. That means it won't go directly on top. If you think about your hands are mirror images of each other. When you put them up, they're identical. But when you try to overlap them, they won't perfectly overlap with each other. They're non-superimposable. That's exactly what enantiomers are. So if we take this molecule on the right and we rotate it 180 degrees so that the OH group is on the right and that our hydrogen group is on the left, well, if we're rotating it 180 degrees, this group in the back is now going to be in the front. So it won't superimpose with this OH group in the back. These are enantiomers. And there's a couple ways you can figure it out. The first is the way that we just looked at. You can draw its complete mirror image, and that's going to be its enantiomer. The second way is to flip all of our regions. What I mean by this is we're going to keep our chiral carbon, and we're going to keep our fluorine and our chlorine that are here, but this OH group, this alcohol group that's going into the board, we're going to make it come out of the board. And this hydrogen that was originally coming out of the board, coming towards us with this wedge, we're now going to give it dashes and put it back into the board. These are also enantiomers. And it's just a different method of deriving it. Now, if we take our original example with our OH group rotated 180 degrees, that OH group is going to be in the front. And this hydrogen, when it's rotated 180 degrees, is going to be in the back. And that turns out that it's exactly what we drew here. Let's look at this molecule now. This is 2-methyl-butane. So if we draw its mirror image, we're going to draw its enantiomer. So if we just copy it exactly how it is, these two would be enantiomers of each other. If we try to superimpose, if we try to put them on top of each other to see if they match, we would have to rotate this right molecule 180 degrees. Now when we do that, this wedge, which is originally protruding, it's coming out of the board. When we flip it, it's going out in the other direction, which in our reference is going to be into the board. So since this molecule has a wedge coming out at that location, this one is going to have a dash. And again, we can draw these enantiomers either by reflecting it across the y-axis or by just flipping all of our wedges and dashes. So we can also draw the enantiomer like that. So if we look at our right image, this right mirror image, and we flipped it 180 degrees, we were rotating it 180 degrees across the y-axis, we're going to end up with this, which is exactly the same as this. These are both ways we can derive enantiomers. Let's look at another example. If we have this pentane and we attach a chlorine here and a bromine here, try to draw the enantiomer of this compound. Now you can do it either way that we've looked at. One, you can draw the mirror image. So if we draw this mirrored pentane, our bromine is going to be out here, and our chlorine is going to be back here. The exact mirror image. This is a valid way to draw the enantiomer. The other way, again, is to just flip all of our wedges and dashes. So we can also draw the enantiomer by redrawing the original structure, but now our bromine is in the back and our chlorine is in the front on a wedge. Now let's look at 3-methyl pentane. So here, if we were to draw the mirror image, it turns out it's the exact same as the original. But how can that be the case? Well, these aren't enantiomers because this carbon here is not a chiral carbon. The carbon, for an enantiomer, we need to have a chiral center or a chiral carbon, meaning that the carbon has to be bonded to 4 different bonding groups. This carbon here in the center is bonded to a hydrogen, and this hydrogen is dashed. It's bonded to a methyl group with a wedge. And then on the left and right sides, we have one ethane group, another ethane group. So we have 2 ethyl groups here. Meaning that this carbon is not chiral, so its mirror image is not going to be its enantiomer. It won't have an enantiomer because we need chiral carbons to make enantiomers.